filtration and reabsorption. Two different but similar terms, but you still need to know what they mean. If this is your capillary, okay, and this over here, if this is your capillary, this is the arterial end. See that? Yeah. And this is going to be the venous end. Okay? This is the capillary. That means the either side of this is going to be the interstitial area. Now, if fluid goes into the interstitial area, okay, that is going to be filtration. You're filtrating out the fluid in those areas. If that fluid over here needs to come back, then that's going to be reabsorption. You're reabsorbing it back to where it came from. Okay? So that's reabsorption, that's filtration. Okay? So let's clear this up. Okay. Write it. So, kind of jumped the gun a little bit, but you guys know what interstitial tissue is. So we have intracellular fluid, which is any fluid that's found in the cells, and that's where most of your fluid is. Your body is 60% water. Most of that is in the intracellular space. Then what's left is anything outside the cells. So it's kind of divided two ways. It's either in the extracellular fluid, ECF, but we have the interstitial fluid, where the interstitial area is what I was telling you about is over here. So technically, extracellular fluid and interstitial fluid, they're all extracellular fluid, right? It's all outside the cells. All right? So just so you can see it, we have here, here's our blood vessel, and here's our cells up here. So we have the interstitial fluid that's going to be basically in between the blood vessel and the cells. So you can see what that is. And what we're talking about over here, interstitial fluid, is here. Okay? The cells is kind of like where that board is up there. All right? Just so you can get oriented to this. And we'll be using those abbreviations quite often throughout the rest of the semester and probably the rest of your careers. Okay, so we have these Starling's forces. Again, this should have been all taught in anatomy and physiology. But let's, I think this is crucial for us to review this. So we have hydrostatic pressure and oncotic pressure. This oncotic pressure is sometimes referred to as osmotic pressure. Okay, it's being drawn in there. We'll get into it in a few. So let's talk about hydrostatic pressure first. This one tends to be easier to understand than the oncotic pressure. So hydrostatic pressure, as the name implies, it's dealing with water. It's dealing with water pressure, hydro, right? So that's basically your blood pressure. So what's going to happen here is this. The fluid that just came from, like the blood that just came from your heart, goes into your arteries and eventually goes into your capillaries. So there's going to be a lot of hydrostatic pressure here because that's closest to the heart, okay? And what will happen is there's a lot of pressure out here. Now, you do have hydrostatic pressure in the interstitial area. So there's hydrostatic pressure here and there's hydrostatic pressure here. But the one where the blood is coming into the capillary, it's greatest over here. So we have greater hydrostatic pressure in the capillary than there is over here, at least on the arterial end. So because of that, there's more hydrostatic pressure here than over here. The fluid tends to go out to that area, okay? Now, when I say the fluid, it's the fluid that goes out. Proteins don't go out there. Big things don't. Red blood cells, they just don't go out there. So they're kind of getting, as we used, filtered out there, right? So the fluid just gets filtered out there, leaving all the bigger stuff here. red blood cells, the big proteins like albumin. All right, that's the big one. So what will happen is it's higher hydrostatic pressure here, lower over here, so it's pushing it that way. But look what's happening. As it's pushing it out there, gradually the fluid is going to be going out there, or I'm sorry, there's going to be more out there than there is over here. Is it not? Right? You have a lot here and a little over here, but you're pushing it up there. So now you're going to have a lot of it out there. Soon enough, maybe midway through here, then the hydrostatic pressure in the interstitial area is going to be higher than the hydrostatic pressure in the capillary. So it's going to reabsorb. It's going to go back into here. Does that make sense? Right? So the hydrostatic pressure in the capillary is going to be very high at the arterial end, but it's going to be very low when it gets towards the venous end. Right? It's going to gradually go this way. Up here, it's going to be, the hydrostatic pressure in the interstitial area is going to be very low at the arterial end, and it's going to be greater up here. So great up here, where it's going to push it back in here. Okay? So that's what's happened. That's hydrostatic pressure. Now, another thing about the hydrostatic pressure, we talked about this, is that if, let's say, 30 liters goes out into this interstitial area, then you would expect 30 liters to get reabsorbed back in the capillary. But it doesn't work out that way because of the physics and other things that's over the scope of this course, that 30 liters goes out that way, only 21 liters comes back. And the reason, the way we can get those extra 3 liters, well, that's the purpose of the lymphatics. You have these lymphatics over there that are going to take up that extra 3 liters that couldn't go back into the capillaries. Okay? So 30 liters goes out, 27 come back. The lymphatics will eventually bring that extra 3 liters back into the circulation. But what's nice about the lymphatics, as you learned, is that before it goes back into the blood system, in the circulatory system, they have to go through lymphatic tissues, lymph nodes and spleen and tonsils. And as it goes through there, that's where they're going to be examined. That tissue is going to be examined to make sure there's no any bacteria in there, cancer cells, and so forth, that is going to be looked at with all our white blood cells and destroying whatever doesn't belong before it goes back into the system. All right? So it's kind of our customs, like at the airport and stuff. It's like, you want to come back to America, well, we have to go through customs to make sure you're not bringing any drugs and knives and guns and all that stuff. And if everything looks clear, we'll put you back into America. Everything looks clear, you put it back into the system. So that's how this is. That's how all our fluid does get checked. It eventually will get checked by the lymph nodes because of this extra system up here, the lymphatics. Okay? Questions about that? All right. So that's what's happening over here, and that's hydrostatic pressure. All right. Let's see what I've got here. So higher at the arterial ends of the capillaries tends to push the fluid into the interstitial tissues, and then it's going to be lower at the venous ends of the capillaries, and it tends to reabsorb it, getting it back into the capillaries, leaving about 3 liters out there that the lymphatics are going to take back. Okay? Now you can imagine, we're going to start talking about edema and stuff. If there's any clog up here with the lymphatics, then the fluid is going to stay up here, that extra 3 liters. It can't come back here because of the way the system's run, so therefore the interstitial area tends to have a lot more fluid. That's one way we could get edema, and we'll be talking about edema in a few. Okay? So again, just so you see it, you've seen this picture before. So here's your capillary bed. Here's the arterial end. This is the venous end. All right? What happens is the fluid gets filtered out there, 30 liters, and then 27 liters can actually come back into the capillaries of the venous end. But there's 3 liters here that can't go back because of the way the physics are. That has to go back through the lymphatic system, this yellow area, goes through all the lymph nodes before it goes back in the circulatory system to take out any of the cancer cells and the bacteria, viruses, whatever it needs to do. And then once it's cleared, it goes into the venous system and then it goes back into the circulation. Okay? So it's not too bad. Not too bad. It's a nice system. All right, so now let's talk about oncotic pressure. All right, so I got to erase this. Okay. A little bit more to this one, but it's not bad. It's not bad. Okay. So oncotic pressure. So do you see that this hydrostatic pressure is a pushing force? Right? It's pushing fluid that way, it's pushing fluid this way. Well, this oncotic pressure, which is also known as colloid, oncotic, or osmotic pressure, okay? This is osmotic pressure. This is more of a pushing force, okay? It's going to draw things to them, okay? So it's not pushing, I'm sorry, it's more of a pulling force. It's going to pull things towards them. And this is where we got to talk about with albumin, proteins. Okay? So, let's say there are, and we use albumin as our proteins. It's easier to understand with that, but there's all kinds of proteins. So let's say we have albumin here, all right, these proteins that won't be pushed into the fluid. They can't get through those capillary beds. Okay? So you have these rather large molecules, proteins in here. Okay? Now, right now, if we only have 2 proteins in here, okay, what would you say is more concentrated? This area in the capillary or the interstitial area? What is more concentrated if we have, let's say, I'll make this 8. If we have 8 molecules of albumin proteins that are in the capillaries, but only 2 up there. Where is more concentrated? Here or here? We're concentrated here, right? Okay? So that means that up here there's less concentrated. All right? However, what's happening over here is that right now there is no fluid up here. Hydrostatic pressure and oncotic pressure are going to happen at the same time. So what I told you about with hydrostatic pressure, that's what's going to happen, but let's talk about just before hydrostatic pressure occurs. Right now, there is a little bit of fluid up here. Hydrostatic pressure didn't kick in yet. Over here, there's a lot of fluid. So even though there's 2 molecules up here of protein, whatever it is, protein, there's a lot here. If there's very little water up here, then right now this is going to be very concentrated because there's 2 molecules here, but maybe, and I'm just giving you numbers, maybe there's 4 molecules of water. You have 2 molecules of proteins, 4 molecules of water. It's a 2 to 4. But in here, since all the water is still in here, you could have, I don't know, 1,000 molecules of water here, but only 8 molecules of albumin or proteins here. So what I'm saying is it's more dilute here and it's more concentrated up here, right? And because of that, we have to pull more water up here. Water is going to go to where there's more solute or more concentration of solute. There's a higher concentration up here than there is here at the beginning of the capillary bed, at the beginning where the arterial end is. So what will happen is fluid wants to go where there's more concentration. Okay? So there's going to be a pulling of oncotic pressure going towards the interstitial area because it's very concentrated. So what the water wants to do is to dilute it so that it becomes a little bit more like this. Is that clear? Okay? So right now, water is going to go out there. Now, we're not talking about hydrostatic pressure. That's happening too, but we're just isolating, just focusing on oncotic or osmotic pressure. Osmotic concentration, that's what osmotic means. So it's going to where there's a low concentration to a high concentration of these protein molecules, okay? So what's happening is it's going that way, but gradually you're losing all the water over here and you're putting all the water up here. So you're making this more concentrated by taking out this water from the capillary and you're putting it in where the interstitial area is. Does that make sense, right? You're gradually making this more concentrated, which was over here dilute. Well, as it gets about midway over here, now this gets by this time with all the water that just came up here halfway through, now this area has gotten more dilute, and down here, since we drew all the water up there, this is more concentrated. So it's going to go reverse. Make sense? Okay? So what we have over here is, we're clear with that, right? That it's highly concentrated it's highly concentrated up here and less concentrated over here at the beginning of where the arterial end is of the capillaries. So what's going to happen is it's going to draw, right? Pull more water up here to make this more dilute. As you pull more water up here, this is going to become more concentrated. Keep in mind, these purple dots are proteins. They cannot get through the wall of the capillary. So they're going to stay there. The water is the only thing that can pass through there. So the water is going to go that way. When you get halfway through, now this is going to be more dilute because there's less water here. This is more concentrated. So it's going to go the opposite way. It's kind of like a wave, right? It's going to go whoosh, right? It's going to go all up there, and then it's going to come back. Okay? So, large proteins, molecules, albumin is a good example, and we're going to use that when you put that in a person's bag. We'll get into that about beam and stuff. All right? These large proteins, albumin, do not freely pass through the capillary walls, and these proteins exert this attraction force, a pulling force, all right, into the site they are occupying. Okay? Fluid needs to go to the area where the higher concentration of those larger molecules are. Like I said, there's less water here, but there's more proteins at this point compared to how much water is up there. All right? So the water is going to go from a dilute area to a concentrated area. Water follows solute. Water is going to go where there's a higher concentration of solutes or a higher concentration of proteins. Not the number of proteins, but in comparison to water, there's more proteins than there is water, higher concentration. Okay? So, the fluid movement is going to go like this. Let me write this one more time. So if we have hydrostatic pressure in a capillary, hydrostatic pressure in a capillary is going to be very high at the arterial end. But gradually, it's going to go down, right? That's the blood pressure. Here, in the interstitial area, the hydrostatic pressure is going to be very low at the arterial end, but very high at the venous end. Water is being pushed up there. So as water goes more up there, it's going to gradually get higher and higher, the hydrostatic pressure, and it's going to push it down here because it's going down low. Likewise, the oncotic pressure at the arterial end in the capillary, the oncotic pressure is going to be very low here, but it'll gradually get higher. In the interstitial area, the oncotic pressure is going to be very high, but gradually going low. since the oncotic pressure is high up here, water will be drawn to that area. More water, more water, more water. Now it's getting more dilute here, and then it's going to go this way because it'll be pulled into the capillaries. So again, hydrostatic pressure in the capillary will be very high at the arterial end, but gradually go low to the venous end. The hydrostatic pressure in the interstitial tissue is going to be very low at the arterial end, but gradually going to get higher at the venous end. Okay? Sound good? Right, that's what I just put there. All right? And this is showing the same thing in a picture form. See that, all right? So the direction and the amount of fluid depends upon the difference between the capillary hydrostatic pressure and the capillary oncotic pressure. See, the fluid is going into the interstitial area at the arterial end by both the hydrostatic pressure and the oncotic pressure. The hydrostatic pressure is going to push it into the interstitial area. The oncotic pressure of the interstitial area is going to pull it into there. So we're using both of these pressures to get the water into the interstitial area. Why? We don't have to do it. It's just nature. It's just physics. It's going to do that. All right? But we need to understand it so that we can understand why there's going to be leftover fluid here, first of all, the 3 liters. And also, how do you explain about diseases, which is the name of the course, pathophysiology. Why would you get edema in certain instances? Okay? So, hydrostatic pressure in the capillary, pressure of the blood against the capillary walls, right? That's the blood pressure itself. And it tends to push the fluids into that area, into the interstitial area. It's greater at the arterial end, and it gradually gets less. The oncotic pressure draws the water towards those proteins, okay, where there's a greater concentration of proteins, and that's what's happening there, okay? So, in summary, at the arterial end, again, the same thing. The arterial end of the capillary bed, hydrostatic forces dominate, so therefore it's going to push it out. At the venous end, the oncotic pressure forces in the capillary are going to pull it into the capillary. Okay? All right? More fluids, and this is where the lymphatic system. All right? And again, this is just showing you the same principle about osmotic or oncotic pressure, which way it goes into the interstitial area, how it gets back. Again, about 10% or so is going to go back to the circulation by the lymphatics.